Hello, my name is Muhammad Irfan bin Rashid, 2013928445. I will present about my assignment 1B for antenna and propagation. This is my first antenna, dipole antenna. A dipole antenna is a type of RF antenna that includes two conductive elements like wires or rod, where the metal wire length is half of the highest wavelength approximately in free space at the operation of frequency. At the center of the antenna, the conductive material are separated through an insulator, which is called an antenna section. The RF voltage source is given to the middle of the antenna, then the voltage and current supplying throughout the two conductive elements generate an electromagnetic or radio signal, and this signal is radiated outside of the antenna. At the center of the antenna, the voltage is minimum and the current is maximum, whereas the voltage is maximum and current is minimum at the dipole antenna to end. Neglecting electrical efficiency, the antenna gain is equal to directive gain, which is 1.5 or 1.76 dBi for a short dipole, increasing to 1.64 or 2.15 dBi for half-wave dipole. For a 5/4 wave dipole, the gain further increases to about 5.2 dBi, making this length desirable for the reason even though the antenna is then off resonance. Longer dipole than that have radiation patterns that are multi-lobe with poorer gain. Unless they are much longer, even point along the strongest lobe. Horn antenna. A horn antenna is a type of aperture antenna which is specially designed for microwave frequencies. The end of the antenna is widened or in the horn shape. Because this structure, there is larger directivity, so that the emitted signal can be easily transmitted to long distance. Horn antenna operate in microwave frequency, so the frequency range of this antenna is super high or ultra high, which range from 300 MHz until 30 GHz. Horn antenna often have a directional radiation pattern with a high antenna gain, which can range up to 25 dB in some cases, with 10 until 20 dB being typical. Horn antenna have a wide impedance bandwidth, implying that the input impedance is slowly varying over a wide frequency range. The gain of horn antenna often increases as the frequency of operation is increased. This is because the size of the horn aperture is always measured in wavelength. At higher frequency, the horn antenna is electrically larger. This is because a higher frequency has a smaller wavelength. Since the horn antenna has a fixed physical, the aperture length is more wavelength across at higher frequency, and a recurring theme in antenna theory is that larger antenna, or in terms of wavelength in size, have higher directivities. Lastly is dish or parabolic antenna. The most well-known reflector antenna is the parabolic reflector antenna, commonly known as a satellite dish antenna. A satellite dish is a telecommunication device used to send and receive microwave signals. It is a parabolic-shaped antenna used for data transmission and broadcasting. Parabolic reflectors typically have a very high gain between 30 until 40 dB and low cross polarization. They also have a reasonable bandwidth, with the fractional bandwidth being at least 5% on commercially available models, and can be very wideband in the case of cube dish, like the Stanford Big Dish above, which can operate from 150 MHz to 1.5 GHz. The smaller dish antenna typically operate somewhere between 2 and 28 GHz. The larger dish can operate in VHF region, 30 until 300 MHz, but typically need to be extremely large at this operating band. The orientation pattern of a parabolic antenna contains a major lobe, which is directed along the axis of propagation, and several small minor lobes. Very narrow beams are possible with this type of reflector. Next is a parameter antenna that I use to calculate, that is operational frequency. F in megahertz is 900 megahertz. Distance D in km, I use 1 between 1 and 20 km. Transmitter head, I use 150 meter. Receiver head 10 meter. Transmitting wave at band at 30 dBm. Dipole 2.15 dB. Horn 25 dB. Dish or parabolic 30 dB. For urban area, this is formula that I use to calculate for pulse loss. The lowest pulse loss is 108.01722 dB, and the highest pulse loss is 147.88937 dB. Next is suburban. This is the formula that I use for pulse loss, and for the pulse loss suburban, the lowest is 108.01722 dB, and the highest is 147.88937 dB. For open rural, this is the formula I use to calculate pulse loss. For pulse loss, the lowest is 108.01722 dB, and the highest is 147.88937 dB. Next is the urban area that we use to calculate for received power that show in graph. The highest for this graph for urban area is -10. That for the power received. Next is a suburban area graph. For this graph, the highest is -10. Next, for upper rural, the highest is between -10 and -20. This is free space path that show graph for the FSPL that I calculate. It shows the highest is between -20 and -50. This is different between urban and free space path loss. It shows that the difference was height different between two. It shows that the power received for the urban is lower than free space path loss. Next is suburban difference between suburban and free space path loss. It shows that very different in these two. Next is upper rural and free space path loss. It shows that the difference is high between these two graphs. This is all for my presentation.